Good morning, everyone. And at the outset, I would like to thank organizers, Professor Yan and Sir Ajith, for giving me this opportunity to be a part of this exciting gathering. Although I'm a kind of alien to this community, but still have some string attached. So I have been introduced to this by Professor Andrea Perali, Nicola Pinto, Meenakshi Sharma, who is a PhD student at University of Camarino, and Matteo Fretto and Natasha De Leo. They are at INRIM, Torino. And this is a team from NPL and the LGA collaboration, where I know this Joris has already explained a little bit about these superconducting actuators, and Jan. So through these people, I came into this community. So I have organized my talk a little bit like to explain my alien status. I came from National Physical Laboratory, what we do in there, and then motivation for this work, and then the position of NBN superconductor, although Joris talked about NB, but later we think if we can move forward with the high TC superconductors, which have the transition temperature a little bit higher than the niobium, then it will be easy for us to develop some simpler cooling systems, right? So at NPL is basically an NMI of our country, where we maintain the primary standards as well as we develop the newer primary standards. So we are the NMI by the Act of Parliament, and we disseminate precision measurement required for the growth of Indian industry and also for the legal metrology need of the country. Right here, we can see that we develop, we have different kind of activity, like superconducting group is there, and then different engineered materials we are developing, biomedical standards we are developing, solar cells we are developing, and we are known as a timekeeper of the country. So we disseminate time, Indian Standard Time from NPL, and so overall, what we say is our Prime Minister is the president of our society, CSIR, under which my lab comes. So he made a statement: metrology is the mirror showing us our standing in the world, the scope for improvement, because we know that how where we need to improve ourselves. So we develop and maintain measurements and calibration standards, and offer metrology service to legal metrology, develop reference materials. This is a bipolar plate developed for the fuel cell. Recently, NCL, one of our sister lab, has shown that bus is running on hydrogen PM fuel cell, and indelible ink, which has been developed at CSIR NPL, which we used in our elections. Right, and these are the recently developed reference material, and I belong to this Bharatiya Nirdeshak Dravya department, which we call Indian reference materials, and we trademark as Bharatiya Nirdeshak Dravya, right? And also to train the large pool of young scientists and industry persons under the Skill India initiative. So science and technology at NPL has been divided into 5 different activities, 6 different activities: physico-mechanical metrology, electrical, electronic metrology, environmental science, and biomedical metrology. Recently, we have developed the large volume collection of PM 2.5. And here, this is a Josephson junction, which we use for this quantum metrology. And in advanced material device metrology, we are developing carbon materials as well as solar cells. We are having the we are developing with NPL UK and BIPM this primary calibration standard for the solar cells as well. And this is a recent precious metal reference material has been launched in 2016 as a Bharatiya Nirdeshak Dravya. Number is BND 4201. And then Indian Standard Time, we are having uncertainty of around plus minus 2.8 nanosecond with this coordinated universal time, which is maintained through the BIPM, as we are the signatory of MRI signatory of BIPM. Right, and we also disseminate our time to IRNSS, which is Indian Regional Navigation Satellite System. So 4 of the satellites are connected to this, and more are going to be connected with this. So this is overall kind of activity which we have at CSIR and PL. And then now, how through my material science activity, we got connected to this LGWA. So in LGWA, as mentioned basically by Joris, that you use the array of high performance these inertial sensors, and you need high sensitivity in sub-decihertz frequency range or decihertz frequency range. And this may be achieved using superconducting sensors. So then we thought about this, can we go through the niobium and niobium nitride? So niobium is having a transition temperature of 9K, and already some of the characterization is going on with the group of Professor Perali and Professor Pinto at University of Camarino, along with the Joris. And recently we have developed these NBN films with high TC of around 17K. And this material has a superconducting gap of 2.5 milli-electron volt and high upper critical field, which makes it very interesting from basic science point of view, as well as from application point of view. So the large superconducting energy gap of this material allows the design of circuits for quantum electrodynamics in terahertz frequency range, and the small coherence length of around 5 nanometer allows us to deposit to have these very thin films having the high TC without having any kind of phase fluctuations. So these films are very useful in single photon detector and photoelectron bolometers. However, challenge is to deposit high quality thin films of the desired stoichiometry. This is really a cumbersome process. So we propose to fabricate high quality NBN film with the high TC and optimization of coil geometry on there. Already day before yesterday, you sent the dimensions for the geometry, and Meenakshi is working and INRIM on developing the mask for the geometries. So as I said, these are the technologies where this NBN is supposed to be play a very important role, like for superconducting radio frequency cavity and quantum information technology, single photon detectors. So if we compare, as we are looking for the alternate to NB or to NBN, there are a list of these materials. So as you can see, for NB, we have a TC of 9 Kelvin. So where we have to develop this cumbersome cooling system. If we go to NBN, which has a TC of 17, yes, this makes our life a little easy to develop better with those cooling system at ease. And this rho n, this is basically normal state resistivity of 2 micro ohm centimeter, indicating that NBN has a low granularity and the mechanical properties are very good. So we can easily develop those coil geometries in there. On the other hand, challenge is there because we have some kind of a granularity which gives challenge to make this coil geometry while doing the lithography. On this high lower critical field of NB, which is a very good feature from application point of view. As you can see that you can have a full Meissner state in a wide range of superconducting phase diagram. So that gives you a better thing. And then you have a short penetration depth. This indicates that your magnetic field, which we have a very thin skin of superconductor where magnetic field can penetrate into, right? So these are the advantages of NBN. However, on the other hand, well, we don't have this kind of advantage, but other advantages are there, that we have high upper critical field for NBN. And because of this high upper critical field, you can develop your devices which can work in a very high, under very high magnetic field. And still you have the superconductivity, and high TC gives us like at a higher temperature, we reduce the thermal fluctuations, right? So these are the advantages of NBN. On the other hand, the coherence length, a small coherence length, this allows us to have superconducting phase, means like a transition temperature of around 14 Kelvin in thin film of around 5 nanometer. So these are some of the advantages. And later on, we can think of, as you were saying, the temperature there is around or less than 40K. So MGB2 looks to be a better candidate in there. So once we optimize things in there, we can move, we can look for an opportunity to work with the MGB2 kind of materials. So, sorry. So here you can see this is my sputtering system, which is having this load lock in here. And then we transfer this sample to this chamber and we deposit NBN, and there we can do the metallization as well. So this is in situ, we can develop different kind of heterostructure in there. But right now I'm only concentrating with the deposition of this NBN. And there are not many factors which affect the superconducting behavior of this NBN, that is substrate type, for example, MgO, SiO2, C-cut aluminum oxide and R-cut, and then the substrate temperature, deposition rate, and then argon to, very important one is argon to nitrogen ratio, because we are using the reactive sputtering in there. So argon to nitrogen ratio plays a very important role. And then is the deposition pressure, because this is critical for defining the phase diagram and phase formation thing in there. And here you can see this, the phase diagram of NBN is highly notorious, but this is a binary phase diagram. And the highest TC we get in this delta phase, cubic delta phase, and we have a very small window. So through this window, we have to optimize our parameters in there. And we have some other these phases. If we are deviating a little bit, we are having little higher nitrogen pressure, or we are having little chamber pressure a little vary, then other phases arises into the films, right? So we have to control these parameters. So these are different kind of phases exist, and we are looking for the cubic delta phase, which has a TC of around 17.6 Kelvin. So to achieve the correct stoichiometry, nitrogen and processing pressure are the two most critical parameters in there. So this is while we were optimizing our this NBN film. So here you can clearly see that we are only obtaining this NBN 200 phase in there. So this is a film of 17 nanometer thickness, and this is a film of 30 nanometer thickness. So as I don't have this RT measurements, I was having magnetic property measurement system, sorry. So this was the characterization, and this the lattice parameter 8.44 nanometer clearly indicating that I'm making this cubic phase of NBN only. And this is 2 micron by 2 micron scale. We are having this roughness. So roughness is around 0.217 nanometer, which is more or less equal to the roughness which I have of my substrate MgO. So I'm having quite uniform thin film deposited onto the MgO substrate. And then we did this ZFC MT, and there we can see that for the 70 nanometer thin film, we are having a TC of around 12.7 Kelvin, up to 2000 arrested. This went up to like a 10. So as you see with the magnetic field we are applying, the TC goes down. So up to 10 Kelvin we achieved in here. These things were while we were optimizing our parameters, right? And when we optimized our parameter, then after that, we sent those samples to the NRIM, And this is, so Meenakshi was working there to develop some kind of a Hallberg geometry for making electrical characterization. Right, so she was using laser lithography, where you can develop the structure of the dimension around 1 micron. And if you were looking for the higher precision, like 10 nanometer structures you want to develop, then the electron beam lithography we are using. At NPL, we are also procuring this electron beam lithography now. So we can directly send those samples to this University of Cameroon. So this is the process, basically how we develop those structures. Right, we are making some kind of mask. So we deposit this photoresist onto the wafer, and after deposition, then we exposing with the mask. Then we bake our photoresist, and then after exposure, we develop this mask and develop this kind of a structure. So whatever kind of structure you want to develop, we can have those kind of mask in there. For example, this is the Hallberg geometry, which Meenakshi has developed for having the IV characteristic measurements, right? And these are the electrical transport measurement system, where she has measured all kind of those IV characteristic and transition temperature. You can cool this up to 4 Kelvin, and this magnet of 1 Tesla is there, where they have done the measurements under the magnetic field of some millitesla. Okay, so this out of this particular work, this optimization work of NB thin film, we published recently this complex phase fluctuation effect correlated with granularity and superconductivity nanofilms. So because our theme was not towards the device, towards the fundamental physics. So we were looking for some kind of a quantum phenomena in there. So here, as you can see, we deposited NB thin films on MgO substrate with different thickness of the film. Your TC varies. So this is what I mentioned before, that this is one of the parameter where we have to control the TC. However, even for 5 nanometer thin film, we are getting a TC around 9 Kelvin in here, right? If we compare this with the SiO2, this NB thin film on SiO2, here you can see we are having a broader transition here. The delta TC is basically, we are having some delta TC in here, where the transition in the case of niobium is pretty good. So some other factors are also playing some role in there. And now you can see in here a clear cut that in the bulk, we call it like when we are having 100 nanometer thin film or the 50 nanometer thin film, we are getting up to this 14.7 Kelvin. And now our interest was somewhere here, where you can see this some quantum fluctuations are taking place at this particular thickness in there, because we are reaching to the thickness of the coherence length, which I was telling you. The coherence length was around 5 nanometers. So we are having a thickness of around 5 nanometers. So the quantum phenomena are very much prominent in here. So variation of TC as a function of thickness, if you can see on different this, on MgO, we are having a systematic variation in TC, like up to the film of 40 nanometer or 50 nanometer, we are getting 14.4 Kelvin. This is with the thickness you are having on silicon. So in this case, we are comparing, this work has been done by Professor Nicola Pinto, and he published it. And this is the work in our collaboration, basically. So you can see that on MgO, we are having a systematic work, otherwise some scattering is there. Now, very important parameter in there is the critical current density. So the critical current density, a very nice phenomena we can see there, because the quantum phenomena are very much prominent in here. So as you are decreasing the thickness, right, then your current density increasing, and there is a crossover point. So we call it like three-dimensional to two-dimensional, two-dimensional to three-dimensional crossover, and your current density is again increasing in here. While in case of niobium, your current density is continuously decreasing after a certain thickness. So this is what actually one of the important point in here, where because we need the higher current density, critical current density for our development of the superconducting coils. Right. So this is all about which I was talking about, and then rest of these things which already Joris has shown. So we are planning for initially these spiral coils, and the geometrical dimensions we are getting for it from Joris. And so these things means I have no idea about this black box, and I will learn a little more from Joris, right? Okay, so in summary, we have been successfully growing NBN thin films with stable TC. They exhibit higher critical current density as compared to niobium films, and work is in progress to optimize the geometry of superconducting coils in the sensor fabrication. So with this, I'm really grateful to our director for extending facilities and resources. And we are grateful to University of Camarino, INRIM, Turin, and LGWA collaboration, especially Jan and Joris, so for giving us this wonderful opportunity. Thank you.
Thank you very much. Are there any questions?
Yes. I was wondering that the broad transitions that you showed, and then when it goes to the bulk, then it's less broad. Do you understand what happens with 25 nanometer? Because that looks a bit off.
Here?
No, the results from the new paper by Meenakshi.
This is
or further back, one more, two more. Yeah, something like this. Yeah. So the green line 25.
Right.
That's much lower suddenly. Do you understand what happened there?
Well, this is a little bit we were not able to understand this. I think this was a deviation because with the thickness, sometime we were not able to control the parameters. And I think because we are sending those samples from here to Italy, so that time I was not able to provide her with another set of samples.
Okay, yeah.
So, but something is little. Andrea must be online, and he can also give an answer for this.
Yeah, maybe Wally maybe does that. I was wondering. So, do I understand correctly? So you go from quite broad delta TC.
This one.
Yeah. To the bulk, which is much narrower. Is that because you have in your deposition you have some granularity, and that becomes less important?
Granularity is one of the reason, as well as some losses are there. You know.
And they become less important
because of the thickness. Your film is really thin there, so the losses get increased at that time.
Yeah. Okay. Thank you very much.
Could you tell us if there is any efforts towards the YBCO and the magnesium diboride?
From our side?
Yeah.
Not yet.
Okay. And
because for me, with this collaboration, I entered to the superconductivity, although my PhD was in superconductivity, but for a long time I was away from this subject.
Okay.
Yeah.
From the instrumentation side, is there any deal breaker in utilizing the high TC superconductors versus niobium?
I don't know if you mentioned that in your talk, but with the deposition, it becomes more difficult, right?
Yeah.
I don't know if you mentioned that in your talk already. Maybe somebody should.
So the way I view that is, so if we use a niobium test mass and we want to use the superconductivity of niobium, then we have to cool down to 5 Kelvin or 4 or 5 Kelvin. Anyway, yeah, okay. But if we use something else, or we deposit NBN surfaces on the niobium or insert a block somehow, then you can circumvent that. And then you just use the mechanical stuff. So if you use silicon, you can just choose what you want. And then it comes down to how good and how easy will it be with the sorption cooler. So will that work? Is it easy to implement that? If yes, then we can cool down and use whatever we want, sort of. But if we can do only ambient temperature, so kind of 40 Kelvin, then we should really look at IPCO.
Cooling mechanism there on the where you can that's power consuming.
Yeah, there's some power consumption. Still.
6.
Yeah, but okay, let's say like this. I mean, the power consumption is more a problem for sound check. For LWA, we can only realize it with a good solution to the power problem already, with plenty of power provided. Because so I think for sound check, it's really something that we have to figure out. But for LWA, we must assume that there's a solution, which brings us 200 watts or so to the setup, and then we're fine.
Craters that we are talking about?
Yeah, so there we are looking. So we will hear more about this from Philip later on. So some of them can be very flat, and actually then they are also colder, it turns out, because the diffusive light it has a harder time to get into the central part of the shadow. So for that matter, you could stick out.
Yeah, is it like a few meters, few tens of meters?
Yeah, it depends. But the problem is, of course, you have to search for the right thing. So the height has to be not too high to sunlight, but then the temperature stability still has to be good. Yeah, we are still searching, but it's a very time-consuming search.
Yeah.
Okay, let us thank speaker for